Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to continue with chapter 1, which we started last week. And so today we are going to discuss fairly extensively hybridization. And then during the course of this discussion, we will be discussing the various ways of writing organic chemical structures. But before I do that, let me make a few announcements. The homework assignment for this week has been posted, and that is the end of chapter 1 questions in OWL. For those of you who have not registered for OWL, if you have problems, you should come and see me after this class. And the deadline for the homework assignment, which is online, is Sunday, September 8th at 11 p.m. To assist you in doing this homework, I have also posted the online review session for chapter 1, our end of questions, which we did last year. So if you take a look at this webcast that I posted in Blackboard, that should assist you in doing your homework assignment. For those of you who may have problem downloading those webcasts from the Blackboard site, just bring me your flash drive, either after the class today or next Thursday, and I will download the webcast into your flash drive. Okay. So once you download into your flash drive, you do not need the internet. Okay. So what I want to do today, I do want us to go over the questions in the quiz that you guys have just taken. Do you want to do that? You want to go over the questions?
Yes.
Okay, very good. Okay, very good. And then after we go over the question, then we will finish with chapter 1. Okay. The first question, let me see here. Maud, can you read it for us?
What is the ground state electronic configuration of sulfur?
Yeah, thank you. Okay, what is the ground state electronic configuration of sulfur? What is the answer to this?
C.
C, everybody says C. C is correct. It sounds to me like everybody got that right. Now, how did you approach this problem? Yes.
All right.
What's the name?
Mecca.
Mecca. Okay, good.
All right. So you said the atomic number was 16.
Right.
So according to the orbital diagram, all you have to do is just keep on filling orbitals until it added to 16, which is also attained by adding the superscripts on each of the numbers.
Excellent. Very good. You know that what you start by knowing, of course, the atomic number of sulfur. In this case, atomic number of sulfur is 16, and then you do know that the different energy levels have orbitals. The first energy level has one orbital, which is S. The second has two orbitals, two sets of orbitals, the S and the P's. And the P's have three suborbitals. So what you do is simply just fill in these orbitals with electrons, knowing fully well that each orbital will take a maximum of 2 electrons. So therefore, if you do that, you end up with sulfur having electronic configuration of 1s2, 2s2, 2p, x2, 2p, y2, 2p, Z2, and then we have 4 more, there are 6 more to go, 6 more electrons to go, and then you simply now say 3s, 2, and 4 more electrons to go. You have 3p, x2, and then 3p, y1, and 3p, z1. And if you do that, that will essentially give you this answer here, which is C, right here. Okay, now, supposing I ask you, how many valence electrons does sulfur have? How many does it have? 6? Very good. Okay. So it says sulfur has 6 valence electrons, and those valence electrons start from which orbital? From the 3, exactly. So therefore you have, for sulfur, this will be the valence shell of sulfur, and since that is the valence shell of sulfur, in other words, the electronic energy level that contains electrons, that is the valence shell, and then in that shell you have a maximum of 6 electrons. 2 here, plus 2, 4, 5, and 6. Okay, so therefore, how many valence electrons does sulfur have? How many valence electrons does sulfur have? How many? 6, exactly. So sulfur has 6 valence electrons. Okay, very good. So let us go to the next one. Okay, well, before I do that, let me go to question number 3. Okay. Kijelin, can you go ahead and read this for us? Okay, thank you. It says, calculate the molecular weight of the compound below. In this case, I do want you to show the your calculation to get full credit. Okay, how do we approach this? Yes. You count the number of carbon atoms first, right? Okay. Okay, how many carbon atoms? 8. Okay, so you count the number of carbon atoms first, right? Which is this here. Let us say this is 1, right? That is 2. That is 3, 4, 5. Let's call this 6. Let's call this 7. And this is 8. Keep in mind, when you, this is what kind of structure is this? This is a skeletal structure. Okay, very good. So this is a skeletal structure, and for skeletal structure, you do not show the carbon atoms, and you do not show the hydrogen atoms, except when the hydrogen atoms are attached to heteroatoms. Okay, in this case, we do not have heteroatoms. For example, oxygen or nitrogen, we don't have them here. So, the first thing we do here, we know the number of carbon atoms, so that is C8. What we want to do here is write the molecular formula, C8. Okay. Now, how many hydrogen atoms do we have here? How many hydrogen atoms do we have?
16.
Let me help you out here. Did you say 16, right? Mm-hmm. Okay. Let's do the counting. Keep in mind, we say that carbon must have 4 bonds all the time, right? The end of a line in skeletal structure is a carbon atom. So therefore, this carbon here must have how many hydrogen atoms? 3. Very good. Okay, and the corner of 2 lines or 3 lines will be also what? A carbon atom. So therefore, since carbon must have 4 bonds, how many hydrogen do you have here? 1. About here, how many hydrogens here? 2. About here, how many hydrogens here? 2. Very good. Here, 1, very good. Okay, here we know it's 3, right? Here, 2. Here, 2 also. Okay, so let's start counting. 3, right here, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? 15, 16, right? So we have 16 hydrogen atoms. So therefore, the complete formula for this will be C8, H16. So therefore, what will be the molecular weight of this compound? You calculate the, you know, the atomic weight for each one of the atoms. Carbon is what? 12, right? So from carbon you have 8 times 12, and what do we have?
96.
96. We have 16 hydrogens. Atomic weight of hydrogen is 1. So we have 16. And what does that give us?
112.
So that's 112 grams per mole. So the molecular weight of this compound is 112 grams per mole. Everybody agree?
Yes.
Okay, very good. Okay, now let us go back to the last one, or the second one. Okay, let me see here. Okay, Mecca, go ahead and read this first.
Alright. Which of the following molecules has a sp3 hybridized carbon atom?
Okay. Which of the following molecules, thank you. Which of the following molecules has sp3 carbon atoms? I know that we did not do this in class, but I did tell you to read to watch the webcast. So we are going to do this today, just for your, to reiterate what you guys have watched in the webcast. Now, what will be the answer to this?
Hey.
A, very good. Okay, how did you get to A?
Alright. It's A because, first off, that's an alkane, so all of them are going to be single bonds. And hybridization comes when there's multiple single bonds. So if I just added them around 1 carbon, I got 4, and I made sp3.
Almost there, almost there. Yes, yes.
The carbon is the stage support atom, and it needs to be a stage support atom to be sp3. It's not the bond, it's the actual atom.
It's, excellent, excellent. In other words, in this case, that is correct. Any carbon that is attached to 4 atoms, any carbon that is attached to 4 atoms will be sp3 hybridized. Okay? So any carbon that is attached to 4 atoms will be sp3 hybridized. We are going to go through this today. For those of you who did not get a chance to watch the video, and most of today, this is what we are going to do. So anyway, keep that in mind. We're coming back to this. Any carbon atom that is attached to 4 atoms will be sp3 hybridized. In this case, if you look at this carbon here, it's attached to hydrogen here, attached to hydrogen here, attached to hydrogen here, and is now also attached to carbon. So this carbon is sp3 hybridized. If you take a look at this carbon here, attached to hydrogen, attached to this hydrogen, and attached to this hydrogen, and also attached to this carbon. So therefore, it is also sp3 hybridized. Okay, so that is mostly what we are going to be doing today. Now, is that clear? Okay. Now let's start with today's lecture. Okay, last week we started with chapter 1, For the most part, we discussed most everything in chapter 1 except for hybridization. So today we are going to discuss hybridization. We also discussed last week the concept of valence bond theory, and we told you that for the valence bond theory, only the valence electrons are used in bonding. In the valence bond theory, we told you only the valence electrons are used in bonding. And also that we have two types of bonding. We have the ionic bonding, and then we have the covalent bonding. We also told you most of the bonding in organic chemistry will be covalent bonding, in which atoms are sharing bonding electrons. Okay. Now, let us go back to electronic configuration of carbon. You know, we have electronic configuration of carbon is 1s2, 2s2, 2p, x1, 2p, y1, okay? And we told you how many valence electrons does carbon have? How many? How many? 4. You see, carbon has 4 valence electrons, which will be in this valence shell right here, electronic shell right here. Now, if we want to represent this ground state electronic configuration using a graphical representation, we could have this. Using a graphical representation, energy here, we have the s orbital, one s orbital with 2 electrons. Then we have the 2s orbital also with 2 electrons. And then we have the 3 2p orbitals. And only 2 of the 2p orbitals has 1 electron each. So what we've done here, this is the graphical representation of this electronic configuration that I was giving you here. So here, we say this here, these 4 electrons here, these are the valence electrons. They are in the 2s orbital and the 2p orbitals. Now, supposing we want to write this same electronic configuration using the atomic orbitals. We say this is energy right here. We told you that the s orbitals are spherical, in other words, are circular right here, with 2 electrons right here. 1s. And similarly, we have the 2s orbital, also spherical, also with 2 electrons. And the p orbitals are dumped bell shape. Okay? And only 2 of them as electrons. So what I've given you here, these are different representations of the same concept. But the point to be made there is if you look at this, the valence electrons which are used for bonding are in the s and the p orbitals. And we know the s and the p orbitals, they are perpendicular to each other. Okay? We have the s orbital, spherical, and the p orbital perpendicular to it, right? We know that. Okay, just keep that in mind for now. Now we also know, showing you the electronic configuration, the graphical electronic configuration of carbon again. These are the valence shell. We also told you that in order for atoms to be stable, they tend to want to form chemical bonds. And for them to form chemical bonds, they want to have a completely filled electronic shell. Completely filled electronic shell. And that, for the most part, is why they want to form bonding, because that gives them stability. So in this particular instance, if carbon is to have a completely filled electronic shell, how many electrons does it need? How many? Because keep in mind that each orbital only take a maximum of 2 electrons. So you say it's 4, it needs 4, right? So therefore, carbon needs 4 electrons in order to have a completely filled valence shell. And because if you put 2 here, 1 here, 1 here, everything will be filled. And as a result, you have 8 electrons. You have 8 electrons in the carbon valence shell. Because of that, we therefore come up with what we refer to as the octet rule. In other words, atoms will engage in covalent bonds in order to have a completely filled valence shell, electronic valence shell. And to do that, they need 8 electrons. So we therefore have what we call the octet rule. Having said all of that, the question now is, you have carbon atom. Let us take a look at carbon atom in this molecule called methane. Yeah. Carbon is right here in the center of the molecule, bonded to 4 hydrogens. And each one of these is a covalent bond. And each one of these bonds, you have 2 electrons. Okay? In other words, this carbon is sharing 2 electrons with this hydrogen in a covalent bond. The same thing happens here, the same thing here, the same thing here. Now, given what we know about the electronic configuration of carbon, now we need to explain why each one of these bonds have the same bond length. In other words, this bond from here to here, from here to here, here to here, and here to here, they have the same bond length. And the bond angle right here is 109.5 degrees. In other words, not 90 degrees, because we told you the p orbitals are perpendicular to the s orbital. So if that is the case, there should be some kind of perpendicular. That is not the case. So therefore, we need to have to explain how this happens. And the explanation for this is what we refer to as the as hybridization. Now, in addition to that, take a look at these 3 molecules here. This molecule we call methane. This we call ethylene. This is the molecule that is used to make polyethylene, you know, those plastic bags you use when you go to the grocery stores. Okay? This is the molecule that is used to make those plastic bags. And we call this acetylene. In this case, in the methane molecule, carbon is bonded to 4 hydrogen atoms. We know this bond angle is 109.5 degrees. The same thing, this bond angle is 109.5 degrees. The same thing, this bond angle, the same thing with this bond angle, 109.5 degrees. In other words, this carbon atom is sitting right in the middle of what we call a tetrahedron. It's sitting right in the middle of a tetrahedron, in which each one of the bonds are the same length, and the bond angles for each carbon-hydrogen bond and another carbon-hydrogen bond is 109.5 degrees. So in this case, we say this carbon here is an sp3 carbon atom because it is bonded to 4 atoms. Okay? Bonded to 4 atoms. sp3 carbon atom. Now, we come to ethylene. Look at ethylene. It's almost like this here. Let me focus the camera on myself. Look at this here. Look at this double carbon. This is a carbon atom here. Another carbon atom here. Think of this as hydrogen. Think of this as hydrogen. This is a methyl group, methyl group. Look at this here. This part of the molecule is flat. It's what we call planar. See, this bond angle here is 120. This is 120. This is 120. If you look from your side, this is what you see. This is flat. Okay? Okay. If I get Miss Howard here, take a look at it, the same thing we see. Here, right? It's flat. It's flat. No matter what, you know, if you look at it from no matter what angle, Miss Howard is looking at it here, right here, right? So that is just like you doing there. If you want to use Mr. Howard, right, it's flat, right? Okay, so now the point is to be made here is, you have this carbon here, this bond angle right here is 120 degrees, this bond angle right here, 120 degrees, and also this bond angle is 120 degrees. We also have to be able to explain that. And also now explain how do we end up with a double bond right here. Keep in mind, carbon must have 4 bonds. Okay? It does have a double bond to this carbon atom. And then it's 2 single bonds to hydrogen atom. The same thing with this carbon. This is 120 degrees bond angle. This 120 degrees bond angle. The same thing here, 120 degrees bond angle. So this molecule here, from the part where the carbon is bonded to carbon, is what we call planar. The geometry is planar. Keep in mind this, we say this was tetrahedron. Okay? So the geometry here, we say is planar, it's flat. So, therefore, this carbon atom that is bonded to only 3 other atoms, we refer to as an sp2 carbon atom. This carbon here, because it is bonded to only 3 other atoms, we say that is an sp2 carbon atom. What kind of hybridization is this carbon?
sp2.
Also sp2. This is also sp2. Okay, the point we made here is anytime a carbon atom is bonded to only 3 other atoms, the hybridization must be what? sp2. Okay? anytime a carbon atom is bonded to 4 other atoms, the hybridization must be sp3. Keep in mind there is a difference between how many atoms it is bonded to and how many bonds it has. All the time it has 4 bonds. Okay, but it may have different number of atoms bonded to it. On the other hand, if we take a look at this molecule here, acetylene, the acetylene molecule, this right here. Look at this carbon atom here. How many atoms is this carbon bonded to? 2. So what kind of hybridization are we going to call this carbon? sp. So we are going to say this is an sp carbon atom. This is an sp carbon atom. However, it is still bonded to, it still does have 4 bonds. So what we need to do now is explain how does this happen. Okay, we now need to explain how do we get sp3 hybridization, and how do we get sp2 hybridization, how do we get the sp hybridization. Okay, so to do that, now just bear with me now, because we are going to, this is going to take us to the end of the session today. Hybridization is very important. Anytime a carbon atom is ready to bond to 4 other atoms, it undergoes what we call hybridization, and hybridization is essentially mixing orbitals. You are mixing orbitals. What we call orbitals mixing. We are mixing orbitals. So what is going to happen here? Keep in mind that the valence electrons of carbon are present in the 2s orbital and the 2p orbitals. So what do they do? The 2s orbital right here, you can see here, and these 3p orbitals right here, they are mixed. But before that mixing takes place, there has got to be what we call electronic promotion. Keep in mind, initially, we have let's just focus on the valence electrons for now, okay? So we have the 2s with 2 electrons. Then we have the 1s, 2p and 2p, 1 electron here and 1 electron here. So the first thing that happens is what we call electronic promotion. That is, for that you need some energy, and that is why for most organic reaction you need to input some energy. It does require some energy. So the first thing that happens, what I would call electronic promotion. One of the orbitals in the s orbital will be promoted to the p orbital because the s orbital has less energy than the p orbital. So there is electronic promotion. So the first thing you get is electronic promotion. Okay, that means you require some energy to do that. Okay, so now you have all of the orbitals now have electrons. 1 electron each. Okay, as a result of electronic promotion. Okay, you follow that? Now, once you get the electronic promotion, take this out. You got all that? So, at this point, we assume electronic promotion. 1 electron is here. 1 electron is here. 1 electron is here. 1 electron is here. So each one of the atomic orbitals have 1 electron each. And now, once you get the electronic promotion, the next thing that happens is orbitals mixing, okay? You mix all of the orbitals together. It's almost like putting them in a bag and just mix them, and then they come out with a brand new set of orbitals. And this brand new set of orbitals is now what we call hybrid orbital. We call sp3, this is now we call sp3 hybrid orbital. Now, each one of the shape of the sp3 hybrid orbital is now completely different from the original shape of the p orbitals or the s orbital. Okay, so now you have 1 electron in each one of those sp3 hybrid orbitals. Yes. Okay, how you got the sp3? What happens? The one s orbital and the 3 p orbitals. This here, this here, this here, and this here. Those are the p orbitals. Those 3. And this s orbital. They are mixed together. Okay, as a result of the mixing, you now come out with a brand new set of orbitals, which we refer to as the hybrid orbitals. And because you are mixing 1 s orbital and 3 of the 2 p orbitals, we therefore refer to the new hybrid orbital as sp3 orbitals. Because what are we doing? We're mixing 1 s and 3 p's. And that is how we come out with sp3 orbitals. You follow that? So that is how we come out with sp3 hybrid orbitals. Each one of those orbitals in this case now have electrons. Now, because of the need of these orbitals to be as far away from each other as possible, they now assume what we call a tetrahedron geometry. In other words, this here, all of these are sp3, this sp3, this sp3, this sp3 right here, this one here, and this sp3. Okay, so this is a carbon atom that is ready to bond to 4 other atoms. It now assumes a completely new hybridization in which this carbon now, those valence electrons now look at this. This is the shape of the valence electrons. So now once you have this carbon atom now, it can now bond to any other atoms. For example, I could now have this carbon here. Let us draw the sp3 hybridized orbital right here. sp3 hybridized orbital. You have to excuse my drawing here. Okay, this will be assumed these are all sp3 hybridized orbitals surrounding carbon atom. And you have hydrogen atom is here. Keep in mind the hydrogen atom, the valence electron in hydrogen is in what orbital? It's in the s orbital. So hydrogen doesn't need hybridization. Okay, so hydrogen is here with 1 electron. Another hydrogen is here, 1 electron. Another hydrogen is here with 1 electron. Another hydrogen is here with 1 electron. Now what do we now have? We now have the bonding. All of those get together. We now have carbon is right here. So we have and now we have the hydrogen come here. The sp3 hybridized orbital of carbon will overlap with the s orbital of hydrogen, s orbital of hydrogen, s orbital of hydrogen, s orbital of hydrogen. So now you have 1 electron here and another 1 electron here. So this bonding here, you now have 2 electrons between them, one in which you have now joined together the s orbital of hydrogen and the sp3 orbital of carbon atom. Okay? So the same thing happens here. sorry, another 2 electrons here, another set of 2 electrons here. Okay, so now, this is now your covalent bonding. In which this carbon atom is sitting in the middle of a tetrahedron. Okay. Now, each one of these bonds, because there is a head-to-head overlap of the bonding orbitals, the s orbital of hydrogen and the sp3 orbital of carbon, we refer to this as a what? Sigma bond. Very good. Very good. Excellent. So we refer to this here as a sigma bond. So we are going to hear or say all of this terminology. So what we are doing here is simply laying the foundation for your future understanding of organic chemistry. This is sigma bond. This is sigma bond. So how many sigma bonds do we have in this molecule called methane? 4. And this is also sigma bond. Okay. So now that is how we form. So we therefore refer to this carbon here as an sp3 hybridized carbon. Okay. And how do we know sp3 hybridized carbon? How do you know sp3 hybridized carbon? If it's bonded to 4 other atoms. That's all you need to know. Okay. Now, we then say, how do we then form the ethylene molecule? Okay, you follow this so far? Okay. Now the question, how do we then explain this? How do we explain that? The fact that this is sp2 carbon and that this part of the molecule is flat. Okay, so we start again. We do hybridization again. We want to use hybridization. So what is the first thing that happens in hybridization of carbon orbitals? Electronic promotion. So we do the electronic promotion. At this point, I am assuming that you guys already know about electronic promotion. Okay, so therefore, what do we have? We now have, this is the case of ethylene. So I am going to now simply say we have those are the p orbitals, and these are the 2 p orbitals, right? After the electronic promotion, we have 1 electron here, 1 electron here, 1 electron here, and 1 electron here. Now, so we now get orbital mixing. Now, in this case, because carbon atom is now getting ready to bond to only 3 other atoms, guess what is going to happen? Only 3 orbitals will mix. Only the one s orbital and 2 of the p orbitals will mix. So therefore, for your orbital mixing, we are going to get this. This here, imagine that this here just mix for your orbital mixing. And then what do we get? We get, yes. Okay. Whenever a carbon atom is getting ready to bond to 3 other atoms, okay? Keep in mind, only getting ready to bond to 3 other atoms. So what it does is simply to mix only 3 of the valence orbitals. In this case, the 3 orbitals that will be mixed will be 1s and 2 of the p orbitals. You follow that? Okay? So if it does that, now we now have an hybrid orbital look very much like this. Okay, so that would be now what we call your sp2 hybrid orbital. Because only two of the p orbitals are mixed, and then one s orbital. So we therefore refer to that as sp2. Now we have left. We see have the p orbitals left, which is this here. And so what do we have? We now have a carbon atom. Now think of this carbon atom. The orbital picture of this carbon atom now looks like this. This carbon looks like this. Right here, you have an sp2 hybridized orbital and sp2 hybridized orbital. Those sp2 hybridized orbital, in order to be as far away from each other as possible, they assume the angle of 120 degrees between them. Okay, because they do want to be as far away from each other as possible. And that is sometimes what we refer to as the valence shell electron pair repulsion. And that as an acronym of VSEPR. Yes, you have a question? Oh, okay. Okay, so we call that VSEPR, for valence shell electron pair repulsion. In other words, electrons in orbitals want to be as far away from each other as possible, and in order to do that, they assume an angle that will make that possible. In this case, the angle that will make that possible is 120 degrees. So this here, this sp2 hybridized orbital will be 120 degrees from each other. Now, in addition to that, what is now missing? We still have the p orbitals. Okay, we have the p orbitals. So think of the sp2 orbitals. The sp2 orbital are right here, right? Now the p orbital is now perpendicular to the sp2 hybridized orbital. Okay, in that case, let us draw it. So now you see I have this here. Okay, so here, this carbon has one electron here. Let's put one electron here. Carbon here. One electron here. One electron here in the sp2 hybridized orbital. One electron here. And the last electron will be in the p orbital right here. The p orbital is the sp2 hybridized orbital. They are in the planar orientation with regard to the nucleus of the carbon atom. Now the p orbital is just perpendicular to them. Okay. Now what is going to happen? This carbon now wants to bond to 3 other atoms. Okay. Let us see now. So this carbon now, what time do we have by the way? So we've got plenty of time. Always going to be plenty of time, right? Mm-hmm. Got 20 more minutes to go. Okay. Let us look at this carbon now that wants to bond to 3 other atoms. Keep in mind we are following this molecule here. We are following this molecule that we call acetylene. Okay? So we have this carbon here as the sp2 hybridized orbital right here, sp2 hybridized orbital right here, sp2 hybridized orbital right here, And it now also have the p orbital right here, p orbital perpendicular to the sp2 hybridized orbital. These are the green are the sp2, and of course the blue is the p orbital. Okay? Okay, good. Each one of these has electrons. Okay, now let us now take a look at this other carbon. Okay, so that carbon also has this, the sp2 hybridized orbital, sp2 hybridized orbital, sp2 hybridized orbital, and it also still has a p orbital that was not part of the hybridization. Okay. So you have one electron here, one electron here, one electron here. Okay. In each of one of these cases, keep in mind this here, the green, this green here is the sp2 hybridized orbital, and the blue is the p orbital. Put the bond in, electron in there. Okay, for clarity, let me get this out of the way. So now let us now have the hydrogen in place. So you have this hydrogen here with an s orbital, and s orbital, okay, another hydrogen here, s orbital, hydrogen, 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 and hydrogen. Each one of the s orbital, of course, has electron also. Okay, so now we have two carbon atoms. Each one of the carbon atoms is an sp2 hybridized carbon, and 4 hydrogen atoms. We now want to form a bond, form bonds, right? To form this molecule called ethylene. Okay, so what happens? They come together, come close enough, and then the orbitals will overlap. The s orbital of the hydrogen will overlap with the sp2 orbital of the carbon, and also in this case, the sp2 hybridized orbital of this carbon will overlap with the sp2 hybridized orbital of this carbon. So what do we have? We now have this. And this carbon here. Okay? So they overlap. And this here, this sp2 here, and sp2 here. And what happens? Oh, let me be consistent here. I want to make this the green carbon. Okay. For consistency, let me take this off. I don't want to confuse you. Make carbon green. So we have this carbon with sp2, and this other carbon here, also with sp2. They overlap. Then you have sp2 orbital of carbon here, another sp2 orbital of carbon here, sp2 of carbon, and sp2 of carbon. So now you have overlap. So what we're giving you here, we are trying to paint the atomic orbital of this molecule, this ethylene molecule. Okay, so you have 2 electrons, 1 electron and 1 electron. They are being shared. The same thing here, you only have 1 electron here, 1 electron here, 1 electron here, and 1 electron here. Now here comes the hydrogen. Hydrogen S orbital is overlapping right here. Overlapping right here. Overlapping right here. Overlapping right here. Also with 1 electron each. Okay, so those electrons have been shared. Now what is missing? We now have everything in place. We are now able to explain the planar geometry. Keep in mind that the bond angle here is 120, 120, 120. Now keep in mind also we still have the p orbitals. Yeah, I'll look at it. Yes, very good. We still have the p orbitals here. P orbitals on that carbon and p orbital on this carbon, perpendicular to the sp2 hybridized orbital. Okay. So we have 1 electron here and 1 electron here. Now what is going to now happen, because carbon needs 4 bonds, there will be what we call a side-to-side overlap. Side to side overlap of the p orbitals, and those side to side overlap becomes what we call the pi bond.
So where's the side to side overlap?
I will show you. I'll use the Greek symbol pi. So now what happens, let me use a color pen. This here overlap with this.
Oh.
It's a side-to-side overlap, all the way down. Side-to-side overlap. And that is the way they share those 2 electrons. But the side-to-side overlap, which we call a pi bond, is not as strong as the sigma bond. The sigma bond is the stronger bond. The pi-to-pi overlap is weaker. This is very important when we get to chemical reaction, because those pi electrons are going to be very, very reactive. Okay? So now we have a side-to-side overlap. So this side-to-side overlap here is what we refer to as a pi bond. And that is how we get it. So therefore, in this molecule, therefore, one of these bonds is a sigma bond, and the other is a pi bond. And this here is a sigma bond. That is symbols for sigma using the Greek symbol. This here is a sigma bond. This here, sigma bond. And also this here, sigma bond. So when you look at the ethylene molecule, how many sigma bonds do we have?
1.
Sigma. Sigma.
Oh, great.
Is it 5?
Oh, total?
Yes, exactly. How many?
5.
We have 1, 2, 3, 4, 5. We have 5. And how many pi bonds do we have? 1. Okay, those pi bonds are the side-to-side overlap, which are much weaker than the face-to-face overlap, direct overlap, which is the sigma bond. Yes. Say that again.
The one in the middle is at the bottom of the big one.
Does it matter which one it is?
Okay, just a minute.
What you say?
You say which one?
Does it matter if it's the top or the bottom?
Oh no, no. Actually, it is from bottom to top. You see, in most books, what they would do is say there is overlap here, there is overlap here, and I don't want to confuse you to think that those are 2 bonds. You see, what we have here is a cross section, so it's almost as if they overlap from top to bottom. Okay, so it doesn't really matter to answer your question that way.
Thank you.
Okay, so therefore, so that is how we now get a double bond, a carbon-carbon double bond. One of those bonds. One is a pi bond and one is a sigma bond. Okay, so now what we've done here is to use hybridization to explain the structure of ethylene In this case, any molecule in which you have a carbon-carbon double bond, we could use this kind of rationale to explain the hybridization. Okay? Okay. So now, the last thing I want to do before we do one problem before we go. How then do we explain the case of formation of acetylene? How then do we explain the case of, I'm going to leave this for you guys to tell me. How do we explain the formation of this? Acetylene. In which now this is a linear molecule. It's a linear molecule. Okay? In this case we have this here, one of these is a pi bond, another one is a pi bond, and the one in the middle at one of those three bonds is a sigma bond. Pi and pi. And one is a sigma bond. And of course, the carbon-hydrogen bond is also a sigma bond. Using the Greek symbol sigma. Now, how do we explain that? Okay, can any one of you help me to explain this? Okay, we know there is going to be electronic promotion. Okay, let us assume that. Okay, the electrons in this s orbital goes to the p orbital. That's electronic promotion. So once it, yes, right.
The extra next line is in the p orbital.
Okay. Okay, very good. Let me draw after the electronic promotion, let us draw the orbitals, right? Okay, so you have this. A case in which a carbon atom is getting ready to bond to two other atoms. Okay? A carbon atom is getting ready to bond to two other atoms. So we have this. Okay, so now we have all these orbitals after the electronic promotion. Okay, go ahead. You're trying to help me out. So now what happens? For the orbitals mixing, what happens?
You're only mixing two orbitals.
Exactly. You only mix two orbitals. And what are those two orbitals? Exactly. So we only mix two orbitals, which is the 1s and one of the p orbitals. Very good. And once you do that, now you also form an hybrid, two hybrid orbitals, okay, which look like the hybrid orbital that we gave you earlier. So you have what we call the sp hybrid orbital. Okay. Now, once you form the sp hybrid orbital, actually you form two of them. Then what happens to the p orbitals? They are still there, right? Okay. So in essence, you form two. You go ahead and form two hybrid orbitals. Well, I tell you what, since they are the same energy, let us put them together. From two sp hybrid orbital, and then you still have your p orbital is in place. Your p orbital is in place. The p orbital is still there. Okay, in which you have electron here, electron here, electron here, electron here. Okay? Those are the p orbitals. Those p orbitals did not undergo hybridization. These two are the p orbitals. Okay. So now let us now take a look at the carbon atoms that want to form acetylene. So that means this carbon atom wants to bond to 2 other atoms. Do I need to go through the formation of that? I think you guys already got the idea, right? We're going to form, right? Okay, but let me just go through it briefly because I do want to work on a couple of problems before we go. Okay, so we have this carbon atom here. This carbon atom is ready to bond to 2 other atoms. We have a carbon atom with sp hybridized orbital, sp orbital. This is also sp orbital. Okay, you also have another carbon atom next to it, also with those orbitals are as far away from each other as possible, and therefore they assume an angle of 180 degrees. This angle here, the bond angle here, right here, is 180 degrees. Because they want to be as far away from each other as possible. The same thing here. Okay? Now, we also know, in this case, hydrogen is still here. Hydrogen is here. Want to bond to those 2 carbon atoms also, and each one of those carbon atoms. You have electron here, electron here, electron here, electron here, electron here, electron here. And then what is missing at this point? What is missing at this point? The p orbitals on each one of those carbon atoms. Okay? So let me take this out for clarity. We're almost there. Okay. We have the p orbital here, p orbital here, p orbital here, p orbital here. The same thing here. Okay. 1 electron each. One electron each. Okay. Now, what is going to happen? They all mix. I mean, they form the covalent bond. So we have our carbon, this carbon with an sp orbital, this carbon with an sp orbital overlap, another sp orbital here, another sp orbital here, and that will overlap with hydrogen on this side and hydrogen on this side. Okay. You have 2 electrons here, 1, 2, 1, 2, 1, 2. Now the p orbitals now, what do they do? The p orbitals now, what do they do? They now form, this p orbital will overlap with this, and this p orbital will overlap with this, and that's how you form your triple bond. Okay, so therefore, what do we have in acetylene? Acetylene, we have a triple bond. We have this sigma bond. We have this sigma bond, and we have a pi bond right here, a pi bond right here, And the one in the middle, we could consider that the sigma bond. So how many sigma bonds do we have in acetylene? 3. And therefore, what is going to tell you, since you have 2 pi bonds in acetylene, it will be more reactive than ethylene, because you have these electrons in 4 electrons in the pi electron system. Okay, so when we come back on Thursday, we have finished chapter 1. When we come back on Thursday, we are going to start chapter 2. But before you go, just before you go, let me draw this. I know I have 2 more minutes. I know you guys are trying to rush me out of my time. Supposing I draw this molecule here. Okay. What if I ask you to give the hybridization of the carbons in this molecule? Let me ask you. Very good. What is the hybridization of this carbon?
SP3.
SP3 about this carbon?
That's SP2.
SP2, this carbon?
SP2.
This carbon?
SP.
What? SP3. About this carbon?
SP.
SP, exactly. About this carbon?
SP.
SP. Okay, at this point we have come to the end of chapter 1, and when I see you on Thursday, we will start with chapter 2.
Alright, that was the lecture.
Oh, by the way, I will be posting this lecture hopefully by tomorrow morning, if I don't post it before I leave tonight. Okay? So I will send you email as soon as I post the lecture. Just a minute. Just a minute.
What are you guys asking about?